Welcome back to the hopefully last part of differential signaling with RS-422, in which we talk mainly about galvanic isolation of your RS-422 transmitters and transceivers, maybe a little tiny bit about why using twisted pair, I forgot that in the basics, and also just a little bit, because that's kind of a religious issue, about shielding. Enjoy! In the last part, card here, link in the description, we talked about a signal return path, grounding, potential differences, and so on. That was the last picture here that I've shown you in that part, and we talked about putting in here 100 ohm resistors in this configuration where your transmitter and your receiver are referenced to mains earth, to alleviate problems that is currents induced by different potentials of your mains earth connections in the ground loop that you created when you run an explicit C ground, or also called a signal return line. Now, if you have a serious isolation failure somewhere in your mains AC net or lightning strikes, and you got a considerable potential difference between your different main earth grounding points, then these resistors will do nothing for you. Quite the contrary, they will kill your receiver and your transmitter. Let's assume we have a potential difference here of 100 volts. Then, the both resistors limit the current, 200 ohms in total, to half an amp. That's not too bad. But you also have a voltage drop of 50 volts across each resistor. Meaning you're lifting your output or your input, depends on the direction of the current, up or down 50 volts. And then it's a bye-bye transmitter and bye-bye whatever is connected after your receiver, and hello magic smoke. And even if you don't run an explicit signal return line and you don't have these 100 ohm resistors and you have 100 volts potential difference between these 2 points, then it's 100 volts through here, through the electronics, the A and B lines, through the electronics, and again here to ground, which is good either. The potential differences don't need to be destructive. Remember, if you go with the voltages on the A and B line at the receiver side, outside plus minus 10 volts, reference to the ground of the receiver will simply stop working. Yeah. But when we galvanically isolate our RS-422 transmission circuitry and line from the rest of the world, we can totally forget about these nasty potential differences. At this point, I have to make a little confession. So on the breakout boards I was using the whole time, I not only have an Renaissance ISL8490 RS-422 transceiver, that's this 8-pin jobby here, but also an Analog Devices AdUM121N digital isolator. So the digital input to the receiver and the digital output from the receiver were all passed through the digital isolator. However, both power supplies of the isolator were of course connected to the 5-volt rail of the Arduino, and both grounds were also connected to the Arduino ground, basically rendering the whole thing here useless as an isolator, really just pathing through the signals. I've modified my breadboard setup here. So the Arduino power rail, Arduino somewhere down there, is going into an isolated DC-DC converter, 5 volts to 5 volts. And the output of that converter is supplying the isolated side on my breakout board. And there's also a 240 ohm resistor. So that's the circuit on my left on my transmitter breadboard. I still have my function generator here, which is referenced to mains earth and goes with a coax cable, which I terminated with 50 ohms to my breadboard. And there the digital signal goes into the digital isolator. But now I have here that isolated DC-DC converter who takes the power rail from the Arduino and creates an isolated 5-volt power supply on the other side. And I use that 5-volt power supply to supply the other side of my digital isolator here, and the signal goes through into my ISL8490 transceiver, which I only use the transmitter part of. And that buggers off via the twisted pair to my right-hand side receiver breadboard. And I also have here my signal return ground or C-line buggering off to the other board. And the secret about that 240 ohm resistor here on the outputs of the isolated DC-DC converter is explained in another video about the peculiarities of these DC-DC converters, unregulated ones. Card here, link in the description. Basically, you have to put a minimum load on the output to keep the 5 volts really at 5 volts and not go beyond 5.5 and to other unacceptable voltage levels. And my transceiver chip is of course also supplied from the isolated side of the DC-DC converter. I did exactly the same changes here on the right side receiver board. Yeah, the probes are a wee bit in the way here. In effect, we almost mirrored the circuit from the transmitter board. Yeah, a few changes, of course. My twisted pair comes in here into the receiver half of the ISL8490, and it goes here into the input of the digital isolator, and that output from the isolator goes to my oscilloscope probe, which is of course again referenced to mains earth. But everything else is basically the same. Oh, and I forgot to draw in the 100 nanofarad decoupling capacitors here between VCC and ground, here between VDD and ground 2, and here between VDD 1 and ground 1. You saw them on the breakout boards. And on the oscilloscope you can see it just works fine. Top trace is the input from my function generator, bottom trace is the output from the digital isolator here on the receiver side. Please note I disconnected the probes measuring the differential pair because my oscilloscope ground is still referenced to mains earth, and having these probes connected would defy the purpose of galvanically isolating my whole RS-422 transmission line here. To measure my differential pairs, I will have again to galvanically isolate my scope using an isolation transformer, which I will do now. Now with the scope galvanically isolated via my crude isolation transformer, card here, link in the description, we can have a look at the differential pair, probes connected again, but please note I disconnected of course the input and output probes, especially connecting the input probe here on the transmitter side would create again a mains earth connection because my function generator is also referenced to mains earth. In part 3 of the details, card here, link in the description, I demonstrated how important the ground connection or signal return line is for an RS-422 transmission line. So let's see what happens if I remove that from my completely isolated transmission line, and yes, something's happening. We saw a little jump here, but overall it doesn't look that bad. Let's have a closer look. And you see, like with the unisolated transmission line, we have now some common mode noise on our differential pairs. Let's change the time scale again so we get a clearer picture and freeze that. And yeah, also again, it's that 43 kilohertz signal, wherever that's coming from. The amplitude of the common mode noise is much smaller than with the unisolated transmission line. This is half a volt or a volt at max, well within what RS-422 can take, but it's still there without the ground line. So a galvanically isolated RS-422 transmission line is less susceptible to a missing signal return than an unisolated one. However, this is still not a operation mode supported by the RS-422 specification. It says you need a signal return, a ground or scene line, as we saw in part 3. To round off that topic, we have now isolated both the transmitter and the receiver, and thus solved all problems associated with potential differences between both sides and possible ground loops created via mains earth and our signal return line. However, to solve these two problems, you don't need to isolate both sides. It's completely sufficient to either isolate just the transmitter or the receiver. But you have to be careful if you use multi-drop, that is one transmitter and several receivers. In that case, you have to isolate each and every receiver. You don't have to isolate the transmitter, because if you isolate the transmitter and not the receivers, you again can have potential differences between the different receivers, and you can also create again ground loops between the different receivers. I link in the description a document that discusses the pros and cons of isolating everything or just the receivers or just the transmitters in detail. Let's talk about twisting pairs now for a bit. In part 1 of the basics, card here if I still have some left and link in the description, we talked about that any electromagnetic interference, as long as you keep your two signal lines very close together, will only introduce common mode noise in your differential signal. And of course, differential signaling like RS-422 is very resilient against common mode noise. But I didn't explain why you would use a twisted pair, and that has in fact nothing to do with common mode interference. Twisting the wires of a differential pair together of course ensures that they stay close together, but there are other ways to do that. In a flat flex cable, for example, the single wires are held close together by the isolation material molded around them. But if we put another conductor parallel to our twisted pair, the advantage of the twisted pair becomes apparent. In part 3 of the details, maybe a card here, but anyway, a link in the description, we saw that the currents that are flowing through the two wires of our differential pair flow in opposite directions, ideally at exactly the same magnitude. Maybe they're a little bit off in practice, okay? But anyway, so our red A line here, when it's close to our parallel conductor, tries to induce a current in that inductor in this direction. And our B line, the blue one, tries to induce, when it's close to the parallel conductor, a current in the opposite direction. And these current induction here should in theory, or could in theory, completely cancel each other out. In practice, they probably don't, but still good enough. That is good enough to avoid or at least dramatically reduce crosstalk between different twisted pairs inside our cable. Yeah, the Cat3 Ethernet cable I used before always contained 4 twisted pairs. But wait, you might say, what if 2 twisted pairs are parallel to each other and exactly, well, in phase or exactly 180 degrees out of phase? Then my red A line from my first twisted pair would induce a consistent current in this direction in the green wire of the second twisted pair, and my blue B line here of the first one would induce a consistent current in this direction in the black wire of the second twisted pair. Let's just say that chances of that happening consistently over extended length of cable are very slim, and cable manufacturers do their best to avoid it, for example, by twisting the single twisted pairs again around each other, mixing things up, so to say. Onwards to our next topic, shielding, and I promise it will be the last. Of course, shielding your transmission line even improves its resilience against outside electromagnetic interference. In the intro I mentioned that I kind of dreaded talking about that issue because it can become a kind of religious thing. Anyway, if some shielding aficionado watches this, and yeah, you will notice that I take a lot of shortcuts and explain a lot of things probably totally wrong, so feel free to leave a lengthy comment below the video to educate the viewers about my mistakes. Anyway, using shielded twisted pair is obviously better than using unshielded twisted pair. Okay, that's statement number 1. And then it gets complicated. I mean, we have to connect that shield somewhere. And here comes rule number 2. A shield should never be connected on both sides, but only on one side. Because if we connected the shields on both sides, for example, to mains earth, we would have created another ground loop. However, if you look at that shielded twisted pair cable here, which is obviously used for Ethernet, you see that the shield is connected to these metal parts around the plug, which make contact to the metal parts or the metal frame of the socket in the switch. And you can expect it's exactly the same at the other end, where it goes into a router or into a PC or somewhere else. So the shield is connected here on both sides. So you obviously can get away with that. And the reason is, if we look here at the ground loop we created, it doesn't really include our signal ground or signal return line. Yeah. Anyway, if you want an A+, don't do that. Now, where should we connect our shield if we don't have mains earth available? In our isolated configuration, we have obviously 2 options. We can connect it to our isolated ground, or we can connect it to our non-isolated ground. And that's kinda, in my opinion, a matter of taste. If your circuitry is inside a metal box not connected to mains earth, then I'll probably go with the signal ground or a connection to that metal box with the shield. If I expect some high voltage transients here along the transmission line, I personally would tend to use the isolated ground. Of course, if your transmitter and or receiver is not isolated, you don't even have that choice. I mean, this just goes through and these two grounds are basically the same, electrically connected. And then there's a case that you maybe for technical reasons or engineering reasons, whatever, connect the shields on both sides to the signal ground. Well, again, don't do that. But if you do that, don't feel too bad about it. There are two problems with that. First of all, we created another ground loop here. The thing is, for a ground loop to be a real problem, not in regards to potential differences, we don't have any here, but in regards to catching electromagnetic interference as a big antenna loop, this is not really a problem, because to catch these electromagnetic fields you need some area in your ground loop, and the area between here on the board we have a little bit, and then during the length of the cable we have a little bit of area, but that's inside the shield, so yeah, you can get away with that. The second and maybe more significant problem here is that you now have two parallel conductors for your signal return line. And basically we saw that the signal return line also carries the signal. And now you carry part of the signal outside on the shield. And that's not the purpose of the shield. You can alleviate that problem maybe a wee bit when you introduce here some resistors, like we did, it's not in that drawing, to main earth with 100 ohms or so that the majority of your ground signal or your signal return really goes through the inside conductor inside the shield. It's not nice, but yeah. Just don't be the guy who says, okay, if I have already here a nice ground connection through the shield, let's delay that ground line here altogether. We don't need that anymore. That's a bad idea. It's a general bad idea to use your shield as a signal return line. And you might say coax cables do the same, but a coax cable are a totally different animal in that regard. Don't be that guy. Finally, I should mention that you can have even more shielding if you want to. If that makes sense for RS-422, I don't know. Anyway, Cat7 cables, for example, have each individual differential pair wrapped in a conductive foil. Please note that these wrappers and the outer shieldings are not really isolated from each other, so electrically it looks like that. Do you have an additional shield between each of the differential pairs, and of course you have the shielding to the outside. That reduces again the crosstalk between the different differential pairs. There are also industrial cables available where you have individually shielded twisted pairs, and the shields are really electrically isolated from each other. So it looks something like that. Of course, you can get those with a complete shield around the whole assembly, also electrically isolated, something like that. So you have the outer shield, and that's isolated from the inner shields. The inner shields are isolated from each other, and inside the inner shields you have your twisted pairs. How to connect the different shields to which grounds or main earth, that's another topic. And that's it for today and for RS-422, at least for now. Who knows? But anyway, after these 6 videos in total, 2 basics, 4 details, you should have enough to implement really good RS-422 communication systems. So, till next time, bye.